Hi, I'm very excited to go through this course titled Tidy Data using R. Before I jump into the course, I'll just give a quick introduction. My name is Abhishek Mukherjee. I am from India, but currently I'm situated in Kentucky, United States. I completed my master's from the University of Pittsburgh in December 2016, and since then I have been working with a healthcare company in the domain of statistics and data science. I've used various statistical software and programming languages such as SAS, R, and Python. Okay, so let's jump back into the course. So this is just a quick high-level uh, topics of what we would go through. We'll start with introduction into tidy data and how do we use the tidyverse package to work with tidy data in R. Then I would go through the concepts of pivoting, separating, and uniting. And we'll also look into how do we deal with missing values in tidy data. And we'll wrap things up by looking at non-tidy data and how do we deal with that in a very high level as well. So first things first, what do we mean by tidy data? Tidy data is a term that is used to define a way of organizing our data in R. There is some work upfront to make our data tidy, but then it pays off as we continue to work with that particular data set. So to work with tidy data in R, we use a package called tidyverse. And when we load this package or install this package, we don't really need to install some of the other packages such as dplyr. Because tidyverse, when we install the tidyverse package, R by default installs some of the other packages such as dplyr. There are many ways to organize a data set, but some ways are better than others, and we would go through that in the next slide as well. In the next slide, I'm going to show some different data sets or data frames, and mostly all of them would have these four variables such as country, year, population, and cases organized in four different ways, and we would see which one or which ones are in a tidy data format and which ones aren't. So as you can see here in the screen, table one has four columns: country, year, cases, and population. In this scenario, cases can be thought of as number of patients with a particular disease. So it can be number of patients with tuberculosis or measles, or even number of patients with uh, COVID-19 cases. So as you can see in table one here, the way we can interpret this data frame is that if we look at the first row here, we can see that for country Afghanistan for the year 1999, the number of cases were 745, and it also had a particular population value for that particular year. Similarly, if we look at the third row in table one, we can see for country Brazil in the year 1999, there were approximately 37,000 cases, and it also had a corresponding population value for that particular year. Now, coming to table two, we can see that there are also four columns, out of which country and year are the same as what we had seen in table one, but now we have two new columns such as type and count. And within the type column, there are two variables, cases and population. So we need to look at what the particular value of the type column is to understand what the value in this count column would actually mean. So basically what I'm trying to say is the way we could interpret a particular row in table 2 would be that, let's say we're looking at the first row. So we would say that for country Afghanistan in the year 1999, there were 745 cases because the uh, count value for that particular column is 745 and the value in the type column is cases. So 745 corresponds to number of cases. Similarly, if you look at the third row here, for country Afghanistan in the year 2000, the number of cases, because the type value for this row is cases, were 2,666. Now, if we go back or look at table 3 here, we can see that table 3 has a different schema altogether. It has country and year column, but now it has a rate column here. So if we did not know what the values of 745 and this value of denominator means, then it's very hard for us to interpret what this rate field or column actually means. Now, if we look at table 4A and 4B, it's even difficult to interpret what these columns mean. For example, in table 4A, the column names are 1999 and 2000, which is very hard to interpret. So can we guess which one is a tidy data set in this scenario? This slide would help us understand what are the characteristics of a tidy data set. So essentially, for a data set or a data frame to be tidy, it has to follow these three rules, such as each variable must have its own column. Number two, each observation must have its own row. And number three, each value must have its own cell. These three rules are interrelated because it's not possible to only satisfy two of the three rules. So understanding this concept is very important. And using these three rules, we can now go back to our slide and check which table in that particular slide was a tidy data set. So here we can see that table 1 is our tidy data set because it's the only table where each column is a variable. So if you look at table 2 here, the variable or the column type has two separate variables within it, like cases and population, which wasn't the case in table 1. In table 1, each column has its own variable. So as a result of this, it's very easy to interpret table 1, whereas in table 2, it's a bit complicated to interpret. Also, the number of rows in table 2 would increase. For example, in table 1, for the country Afghanistan, there were 2 rows, and the information that was conveyed in table 1 using the 2 rows, we had to use 4 rows in table 2. So the data frame size also increased in table 2, and table 2 wasn't that easy to read as we had seen in the previous slide, whereas table 1 is pretty easy to read. And the reason why it's easy to read is because it's in a tidy format. So this brings us to the advantages of making our data tidy. So the number one reason for making our data tidy, like I said, is it's very easy to interpret our data frame. And also, it's a consistent way of storing our data. Now, once our data frame is in a tidy format, it becomes simpler to create different variables or different predictors using the mutate and summary functions, which are part of the dplyr or the tidyverse package in R. We can also easily plot graphs in R using the ggplot package once the data set or the data frame is in a tidy format. If you look at this slide here, because our data set was in a tidy format, we could easily create this new column or variable called rate using the mutate command, and rate can be defined as cases divided by population. Now, if we wanted to calculate the rate of cases in the population per 10,000 people, then we would multiply this rate by 10,000, as we can see in the slide. Also, we could sum up or we could get a sum of or count of cases for the different years in our data set. Similarly, we could sum up the number of cases for the different countries in the data set. This were all possible because our data set was in a tidy format, and hence doing these in R were possible and also pretty simple to do. I'll go through how do we create these counts, and how do we create new variables and plot graphs in R when I do a live screen share of my RStudio screen as well. Similarly, we can also plot the trend of number of cases for the different countries for all the years by using the ggplot command in R. Like I said, I'll go through a live screen share of my RStudio screen where we can look at how we code using the tidyverse package in R. Okay, so to go through the tidy data exercises, I'm going to share my RStudio screen now. Okay, so let's see how we can code using the tidyverse package in R. As you can see, this is the RStudio screen. So to start coding using the tidyverse package, we would first load the tidyverse package. And to do that, we use the library command. So library tidyverse. When we hit run, we can see that once we load the tidyverse package, R by default attaches the package ggplot, which is a package which we can use to plot various graphs in R, and also by default it loads the dplyr package as well. Although R by default loads the ggplot package, I still like to explicitly load the ggplot package. It just helps me to keep track of how many packages I'm loading. And then for this exercise, we are going to use one of R's preloaded dataset, and to access R's preloaded dataset, we first need to load the library called datasets. So that's what we do here. We say library datasets, and in this exercise, we are going to work on the preloaded dataset called iris. So to get access to the iris dataset, we write data and then the name of the dataset. In this case, that is the iris dataset. And then we run this command. So as we can see, the iris dataset has been loaded here. If you click on the iris dataset here, we can see that there is a column called species here. So essentially, this data set is a data set of different species of flowers, and there are various species which we can get an idea by just scrolling through the data set. And also, there are variety of characteristics of the flowers in this data set. They are sepal length, sepal width, petal length, and petal width. Just by looking at this data set, we can see that it is in a tidy format because each column is its own variable, and each row in this data set is its own observation. So each row in this data set is essentially a flower with corresponding values of sepal length, sepal length, petal width, and also we can get to know what species this particular row or this particular flower belongs to. So for example, this first row belongs to the species of flower called Setosa. So let's say we want to summarize this data set in a way where we want to count the total number of flowers in each of the species. Like I said, there are multiple species. If you can scroll through this data set, we can see that after the Setosa species, there's another species called versicolor. So let's say we want to count the number of flowers in each of the species, and we want to also get the mean or the average sepal length and the average sepal width of each of the flowers in the different species. To do that, we can use our summary function. So let's see how we can do that. So let's say that we stored the result in a data set called summary, and then we write the name of the data set called iris, and then we use this operator here. So this operator is called the pipe operator, and essentially it tells R what my next step should be. This is also one of the key programming functionalities when we code using the dplyr package or the tidyverse package. Like I said, it tells R what my next step should be. So here I tell R that I want to start with the iris dataset, and then because I want to get a count of the flowers uh, for each of the different species, I need to group this data set by the species column, which I do by using the group by command or group by function that R has. So once I group by species, um, I want my next step to be to count the number of flowers in the data set. So that's why I use this pipe operator again. So to get a count and to find the mean sepal length and sepal width, like I said, we can use the summary function. Sorry. So we can say summarize um, total. Let's say we name this variable called total. So total is equal to n. So this n function here counts the number of rows in a data set. Um, so because we first have grouped this data set by the species column, this n function will now going to count the total number of rows or the total number of flowers in each of the species, because we have already grouped this data set by the species column before using the summarize function. And like I said, if you want to find the average sepal length and average sepal width, we can create a column called mean sepal length, and we can equate that to, or actually we can find the mean or the average using the mean function that R has. So we want the mean of the sepal length column. So we write mean sepal length. And also let's create another variable called mean sepal width, which is equal to the mean sepal width. So now if we run this command here, we can see that we can see our summary data set here. So once we click it, we can see that uh, the count of total number of flowers in the different species within the data set, and also we have calculated the mean sepal length and mean sepal width for the flowers within the different species that were present in this data set. So now let's say that we want to plot the petal length and petal width for the flowers for the different species in this data set, right? So to plot the petal length and petal width for the flowers, we'll use the ggplot command or the ggplot function. So we can say ggplot, and then the first parameter is actually the name of the data set. So in this case, it is iris, and then, sorry, and then we can write mapping equals AES. AES stands for aesthetics. So here I'm telling our or telling R that my x-axis should be the petal length column, and my y-axis should be the petal width column. I'm sorry. Y-axis should be my petal width column. And I'm going to group this data set by the species column, because we want to plot the petal length and petal width for the different species present in this data set. So I'm going to use color equals the species species column, because we want to color these points with regards or with respect to the species column. And then we are just going to also write or give the geom point function. So essentially, the geom point function in R would um, just plot the data set, like will plot the data in a point structure. So we can just, once we run this, we'll get an idea about why I use this geom point function. So once we run this, here we can see that the x-axis is made by petal length, y-axis is made by petal width, and this graph is colored based on the different species that we had. So that's why I had used the color equal to species command. And as we can see, the different data points in this data set is plotted using a point structure. So that's why I had used the geom point function as well. Okay, so let's go back to our slide deck now. Now, in the part 2 of the lecture, we will go through the concepts of pivoting. So till now, in part 1 of the lecture, we had seen how we can work with a tidy dataset using the tidyverse package in R, and also how we can differentiate a tidy dataset from a bunch of other non-tidy datasets. In the real world, majority of the datasets that we work with would be in a non-tidy format, and our first step would be to convert them to a tidy format. Some of the challenges with the non-tidy dataset are, number one, where one variable might be spread across multiple columns, and number two, where one observation might be spread across multiple rows. So let's deal with them one by one. First, we'll start with the first one, where one variable might be spread across multiple columns, and how do we convert the non-tidy data set to a tidy data set in that scenario. So let me first go back to slide that we had seen earlier. So in this slide, we had concluded that table 1 was in a tidy data set, tidy format, and all the other data sets were in a non-tidy format. So if we take a closer look at table 4a here, we can see that this is in a non-tidy format, and it was very hard to interpret because we didn't really know what the column names 1999 and 2000 meant. So, like I said, one of the challenges in a non-tidy format is when the columns are not variable names, but the values of a variable. What does that essentially mean? So here we can see that these column names like 1999 and 2000, instead of being variables, they're actually names, right? So what we can do is that we can store these names 1999 and 2000 into a new variable called year, and we can store these values present in these two columns 1999 and 2000 into a new column called cases. And by doing that, we will transform this table 4a, which is currently in a non-tidy format, to a tidy format similar to table 1. Let me go back to the pivoting slides. So that transformation we can do by using the pivot longer function. In the pivot longer function in R, we start by the column names on which we want the transformation to take place. So here we want the transformation to take place on column names 1999 and 2000. And because we are transforming these column names together. So we are concatenating these two columns. That's why we use the C letter, which stands for concatenation. And then the next parameter is the names too. So we want the names to transform into a new column called year. So we want these names of 1999 and 2000 to be transformed to a new column called year. And also we want the values, right? Like these are the values to be transformed into a new column called cases. By using the pivot longer function, we make the data sets longer by increasing the number of rows and decreasing the number of columns. Oftentimes, the number of columns may or may not decrease, but by using the pivot longer function, the new data set always has more number of rows than what we started with. So in this scenario, we see how when we use the pivot longer function, how this table 4a on the right-hand side, which was in a non-tidy data set, got transformed into a tidy format called table A after, as you can see on the left-hand side. So as we can see, prior to the transformation, table 4a was in a non-tidy format and had 3 rows. And now after the transformation using pivot longer function, this table 4a has 6 rows. So the number of rows increased, but the number of columns remained the same. But now this table 4a got transformed into a tidy format. The reason is because each column is a variable on its own, and each row is its own observation, and it's much clearer to interpret. Similarly, we can transform table 4b into a tidy format as well, and we would go through these examples in our live screen share of my RStudio screen in just a few minutes. The next transformation function that we need to know is the pivot wider function, and this is essentially used when we are dealing with this problem in a non-tidy data set is where one observation might be spread across multiple rows. So here in this table 2 example, we can see that this column called type had two values within it, like cases and population. So we can transform this table 2 into a tidy format by splitting up this type column um, so that the new data set would have these names here, like case, instead of the type column, it would have columns called cases and population, and the values present in the cases and population would come from this count column. So such kind of transformation is done by, like I said, by using the pivot wider function. So in this scenario, we can see how we can use the pivot wider function. So here we are saying that we want to transform this table 2 where the names in the new transformed data set would come from this type column. So the new transformed data set would have names from the type column. So the names would be cases and population, and the new data set would have its values coming from the corresponding count column. So when we use the pivot wider function, it decreases the number of rows and increases the number of columns. Oftentimes, the number of columns may or may not increase, but the number of rows uh, will decrease for sure. So by doing this pivot wider transformation, we can convert the table 2 to a tidy format similar to table 1 as we had seen in some of our previous slides. I'll go through these examples of pivot wider and pivot longer when I'm going to go through the corresponding exercises by doing a live screen share. Okay, so now let's go through some of the pivoting exercises and examples that we had seen. So to use some of the tables that we had seen in the slide deck, we first need to install or load the package tidyverse because these tables are preloaded in R. So to look at the table 1 that we had seen in the slide deck, we just use data table 1 because, like I said, it's a preloaded table. So if we just click on here, so we can see, or it's better to see it like that. So this was the table 1 that we had seen in our slide deck as well, which was in a tidy format. Similarly, we can load some of the other tables that we had seen, and they are all preloaded in R within the tidyverse package. So we can run table 4a, table 4b, and table 2 as well. So if you just click on each one of them, it'll get loaded in the environment. So let's take a closer look at table 4a first. So table 4a, as we had seen, it's not in a tidy format, and we can convert it into a tidy format by using the pivot longer function. So table 4a, these column names, like we want these column names to be transformed into a column name called year, and we want the values present in table 4b, like these are the values 745, 2666, to be transformed into a column called cases, because by doing this transformation, it would resemble the table 1 structure, which was in a tidy format. So similarly, we can transform table 4B as well. So let's look at table 4B. So table 4B also has these two similar column names of 1999 and 2000, which can be transformed into column name called year. So we want these names to be transformed to year, column name called year, and the values within the dataset 4B to be transformed to a column name called population. So if we take a closer look at table 4B, like these values correspond to the population column in table 1. So if you run these two commands quickly, so we stored the results of transformation of table 4A as updated table 4A, and the results of transformation of table 4B as updated table 4B. So if we click on updated table 4A, as we can see, table 4A has transformed to a tidy format with columns year and cases. Similarly, updated table 4B has been transformed into a tidy format with columns year and population. Now, if we take a closer look, we can join these table 4A and table 4B together to create a similar structure or the same structure actually as table 1. And so we do that by creating a new data set called tidy formatted, where we store the results, and we start with table 4A. And then, like I said, we use this pipe operator, which tells R what the next step should be. So here, the next step is where I'm doing a left join with the updated left join with the updated table 4B data set, and I'm joining on these two columns which correspond to country and year. So essentially, I'm joining table 4A and table 4B on the country and year column, because the country and year column are present in both in table 4B, and the country and year column are present in updated table 4A. So once I run this, command, tidy formatted, if we take a look here, we can see that this tidy formatted has the same structure as table 1. So essentially now we have converted both table 4A and table 4B, which were in non-tidy format, into a tidy formatted data set. So now let's take a closer look at table 2, which we had loaded by using the command data table 2. So table 2, we can see here, has 12 rows, and this one also is in a non-tidy format, but this looks different than what table 4 and table 4B looked. Here we can see that we have a column called type, and type has two values within it, like cases and population. So we can transform this table 2 into a tidy format as well by splitting up this type column into cases and population, and the corresponding values of the cases and population can come from the count column here. So to do that, we use the pivot wider function instead of the pivot longer function, which we had used just a few seconds back. So to do the necessary transformation, we stored the results in a data frame called updated table 2. So updated table 2 would be table 2, and then we do a pivot wider function on table 2, and where we say that the names the names in this new updated table 2 data frame would come from the type column. So essentially, the names of the new updated table 2 would come from this type column, and the values present in the new data frame would come from the count column. So uh, the values would come from this count column. So if you run this real quick, we see that updated table 2 has been transformed into a wide format, right? So it has half the number of rows as table 2, although the number of columns is still the same in this scenario, but in some cases, the number of columns will increase, and that's what we mean by transforming it by using pivot wider. It widens the data set by increasing the number of columns. But in all the cases, when we use a pivot wider, the rows would always decrease. So here we can see that in updated table 2, we have, instead of this type column got transformed into two columns called cases and population. And the values in the cases and population came from the count variable present in the table 2 column. Table to data set. So essentially, we have transformed the table to data set, which was in a non-tidy format, to a tidy format called updated table 2 by using the pivot wider function. Go back to our lecture and look at the concepts of separating and uniting. Separating and uniting are also one of the concepts in which we can convert with the help of which you can convert a non-tidy data set to a tidy data set. So let me first go back to the slide where we had seen all our data sets. Yeah, so here in the slide, we had seen that table 1 was in a tidy format and all the other data sets were in a non-tidy format. And we had seen how we had converted the non-tidy data sets of table 4a and table 4b to a tidy format using the pivot longer function, and we had converted the non-tidy data set table 2 into a tidy data set by using the pivot wider function. Now in this table 3 data set, we have a column called rate, and in this column rate, there is this character separator, or this character string, using which we can split or separate this rate column. So in scenarios like this, where we have a column where we have a string with the help of which we can split a particular column, uh, in those scenarios, we can use the separate function to convert a non-tidy data set into a tidy data set. So let's go back to the slide, the separating slide, it will be clearer. Yeah, so like we had seen in table 3, we have a rate column in which we, like I said, we have this character string, and the left-hand side of this character string denotes the number of cases, and the right-hand side of this character string denotes the population count. So if we split this rate column on this character string, then we can convert this table 3, which is in a non-tidy format, to a tidy format. So to do that, we use the separate function in R. So separate function. So to use the separate function in R, we write separate, and the first parameter is the column name on which the transformation needs to happen. So we pass the rate column because we're transforming the rate column, and then we are splitting rate column into two parts, such as cases and population. So cases and population would be our new column names after the transformation. So we passed cases and population strings into this parameter called into, and then in the sep keyword, or the separator parameter, we pass this character string, which is the division operator in this scenario. So once we run this command in R, we would see that this rate column got transformed into two columns called cases and population, because this is what we had passed into this into operator. And um, the values in this rate column, the left-hand side of this operator or the string got saved or transformed into this cases column, and the right-hand side got transformed into this population column. So using the separate function, we transformed this table 3, which was in a non-tidy format, to a tidy format. When we use the separate function, uh, by default, when the split occurs, R um, has the new columns, which in this scenario are cases and population, as character data sets, which might cause problem downstream, because cases and population are essentially integer columns, as they have integer values stored in them. So to force R to convert them into integer data types, we use this convert parameter, and we uh, give the value of this convert parameter to true. We'll go through these exercises when I do a screen share of my RStudio screen as well. Another usage of this separate function is where we can pass a vector of integers within the separate function, which tells the separate function the positions to split the specified variable at. And the vector of integers must be the same length as the vector provided to the into parameter. Now, this is very important to know. So here in this example, let's say we are splitting the year column in table 3. So this is the year column that we are splitting into two parts, or two columns called century and year, and we give the value of the separator keyword as 2. So this essentially means that when the split occurs on this year column into two parts, century and year, then um, uh, so then let's say, like, if we look at this particular row, right? So for example, in this row, the year column has a value of 1999, and because the separator keyword has the value of 2, so the first two um, positions of this year column, so the first two positions were 19, so the value of 19 gets saved in the century column, and the next two uh, positions has the value of 99, so the value of 99 gets saved in the year column. So let's say if this separator keyword had, instead of 2, had 3, so the first three positions would have been saved in the century column. So the first three positions of this first row for this corresponding year, which is 1999. So the first three positions for this year value of 1999 is 199. So 199 would have been saved in the century column, and just 9 would have been saved in the year column. This would have been the case if the separator keyword had the value of 3. And like I said, we would go through this in the when I do the screen share of my RStudio screen. Similar to, so the next one we look at is the unite function. The unite function is essentially opposite of the separate function, where we combine multiple columns using a single column. So let's say we have created these two columns like century and year in the like we have seen in the previous example. And if you want to collapse these two columns or transform these two columns into a single column called new, then we would use this unite function. So essentially in the unite function, the first parameter is the name of the column that we want to create, and then the next two parameters are the names of the columns on which we want to use or collapse uh, the column set. So we want to unite the column names called century and year and create a new column called new. And here in the separator keyword, we pass just a blank quotation uh, mark because we don't really want any spaces between the columns names. So we don't want spaces between the column names of century and year. So once we run this unite function or this unite command, we would see that the century and the year column get transformed or collapsed into a single column called year called 1999. So because we didn't pass any space, or we said that the separator column as just blank quotation mark, there wasn't any space or any other special character when we did this transformation. Okay, so let me go through my RStudio screen real quick. Okay, so let's go through some of the exercises explaining the concepts of separating and uniting in R. So to use this as well, we first need to download and install the tidyverse package. So to do that, we write library tidyverse as we have been doing so far. So once we load the package tidyverse, we are going to work in this case on the datasets called table 1 and table 3, and both of them, as we had seen, are preloaded within the tidyverse package in R. So to attach or to load the dataset table 1 and table 3, we just need to run or write data table 1 and data table 3. So we run these two commands. And if we just click on table 1 and table 3, we see that we have them saved in this environment. So just to take a quick look at table 3, you can see that table 3 is in a non-tidy format, and we have this rate column here. So as we had seen in the slide, we can convert this non-tidy data set called table 3 into a tidy format by splitting on this rate column, because this rate column has this character string on which we can split on. So let's say we split table, and so in this case, let's say we store the results in a data frame called updated table 3. So updated table 3 is equal to table 3. So I start with table 3, and then I use this pipe operator, which tells R what my next step should be. So I'm telling R that I'm using the separate function as my next step. So in this separate function, I first pass the rate column on which I want to separate or split on, and then I want to create two new columns called cases and population, which is why I pass cases and population as a string as part of my into parameter. And then I want to split or separate on this character that we had seen in this rate column, because the rate column has this character string which I want to split on. So that's why I pass this same character string as part of my separate keyword. So let me first remove this convert parameter and run this as it is. So if I run this now, and if we click on this updated table 3, which we have seen, so we can see that the rate column, which was present in table 3, so this rate column was present in table 3, and now this rate, now this data set has been splitted on this rate column. So in this updated table 3, we can see that the rate column got splitted, and we have created these two columns called cases and population. And the left-hand side of this character string value got saved in the cases, and the right-hand side got saved in this column name called population. Um, so in this way, we transformed this table 3, which was in a non-tidy format, to a tidy format. But if we take a closer look at this updated table 3, we can see that this data type of the column called cases is character, and similarly, data type of this population column is also character. Uh, but essentially, these are integer columns because the values stored in these columns are of integer type. So to force R into storing them as data type of integer, we can pass this convert parameter, and we set this convert parameter to true. So now if you rerun this updated table 3 code here, and then if we click on updated table 3, we would see that instead of character, we now have numeric data type for cases, and we have a numeric data type for the population column as well. So now let's say we want to split table 3, which has the rate column. Let's say we want to split the year column into two parts called century and year. So that's what we're doing. So we are using the separate function on table 3, and then we are on in this separate function we are passing the year column, and then we are splitting into century and year, and in the separate keyword I pass the value of 2. So if I run this code now, so if we look at table 3a, we can see that uh, table 3, which first had just one year column, now got this year column got splitted into two columns called century and year, and the value that was present in the year column got splitted into two parts. So if we look at the first row, the value for the year column was 1999. So because we had used the separate keyword as 2, in the table 3a, the first two positions of 1999, which corresponds to 19, got saved in century column, and the last two positions, which corresponds to 99, got saved in the year column. And the same transformations took place in the other rows as well. Now let's say we change this now. Now let's say instead of passing 2, let's say we pass 3 here in the separator keyword, and then rerun table 3a. Now if we take a look at table 3a, in the century column, we have 199, and in the year column, we just have the number 9. This is because we are passing 3 as the separator keyword. So because we run the separate function on table 3, so in table 3, the first row had the year 1999. So the first 3 values of the position got saved in the century column, and the remaining last value got saved in the year column. So if we take this back to 2 now and just rerun this table 3a, so now it's back to separating on 2 positions. So if we take a look at how the unite function works, so let's say we have this table 3a and we want to unite or collapse century and year and create one single column called new. So to do that, we use the unite function, and then we pass the name of the column that we want to create. In this case, it's new, and then we want to transform on these two columns called century and year, and then we don't want to have any separators. That's why we pass a blank quotation mark. So if we run this and then we take a look at table 3b, we see that table 3a, which had century and year, got converted or united into a single column called new. Let's say we pass a value in this separator parameter. Let's say we pass this underscore uh, character in the separator keyword, and then we rerun table 3b. So then in table 3b, we can see that this new parameter got created with an underscore uh, character between. Okay, so let's continue with our lecture. This is the last part of our lecture dealing with missing values. Sometimes when we are working with a data set, or when we are transforming a data set, we often run into missing values. Primarily, missing values occur in two ways. Number one is we have explicit missing values. So this means that in a data frame or in a data set, we can see that a particular value is flagged with NA. Or number two, we have implicit missing values, which basically means it's not present in the data. So it's not explicitly flagged as NA, but that one particular row may not be present in the data. So that's what we mean by implicit missing values. So in this example data set that we can see here, there are three columns called year, quarter, and return. So if you look at this example here, we can see that the return in the return column for the fourth quarter of the year 2015, we explicitly can see a NA value being flagged here. So this is an example of explicit NA. Now, if we take a closer look at this data set, we can see that for the first quarter of the year 2016, there is no corresponding row in this data set. So that means that the return value for the first quarter of 2016, for the year 2016, is missing from the data set. So that is the meaning of implicit missing values. So the return value for first quarter of 2016 is implicitly missing from the data set. So when we are transforming data, sometimes implicit missing values can become explicit. For example, let's say that we have this data set as we had seen in the previous slide. On this data set, if we apply the pivot wider function, I'm not going to go in depth into how the pivot wider function works because we have gone through the pivot wider function and the pivot longer function in detail in the part 2 of the lecture. So like I said, in this data set, which is already in a tidy format, why is this in a tidy format? Because each column is its own variable and each row is its own observation. So on this data set, if we apply the pivot wider function, then the transformation occurs something like this on the right-hand side of the screen, you can see. So here we can see that this blue outlined NA value, that is the explicit NA value which we had seen in the previous data frame. Like this value is present here. But now we can see that for the year 2016, for the first quarter, there is an explicit NA present here. So this explicit NA got created here because we used a pivot wider function on this data set. So the NA value that was not explicitly present here for the first quarter of 2016 is now explicitly present in this transformed data set. Another function that can be used when NAs are present is called the complete function. Basically, this function takes a set of columns and finds the set of all unique combinations. So for example, in the same data set as were seeing, let's say we apply the complete function on the year and the quarter columns. We can then see that the blue NA outline box was already explicitly present in the previous data set, but now we can see that explicitly there is a row being created for the first quarter of the year 2016, and we can see that now there is an explicit NA value in the return column, which wasn't there in the original data frame, as the original data frame didn't have any record for the first quarter of the year 2016. It started from the second quarter of 2016. So with the complete function, it creates a set of unique combinations. And in this scenario, it created a unique combination for year and quarter columns because we passed the year and the quarter column in the complete function. Another function that can help us deal with NA values is the fill function. It basically takes a set of columns where we want the missing values to be replaced by the last non-missing value. So in this example data frame on the left-hand side, we can see that we have a person column which has two NA values here, or explicit NA values here. And then if we use the fill function on this data set, primarily if we use the fill function on this column called person, so we can see that these explicit NA values that we were seeing in the original data frame got filled by the name Derek Whitmore, which was the last non-missing value in this data frame. Okay, so let's go over some of the missing value exercises. For this scenario, I'm going to use the air quality dataset. Air quality is a preloaded dataset in R. So to use that, I'm first going to load the tidyverse package using library tidyverse command. Then I'm going to attach the air quality dataset in this environment by using data air quality command. I'm going to click on this dataset. So if you take a quick look at this dataset, we can see that this dataset has relevant columns related to air quality for different days of different months. And we can see that we have several explicit NA columns, as I've highlighted here. So how do we deal with these NA columns or NA values? As we take a quick look at this data set or quick scroll through this data set, we can see that this data set has only numeric columns. So let's say the first way that we want to tackle these NA values is we want to replace all the NA values in the entire data set with 0. So to go about doing that, we use the replace function in R. The first parameter of the replace function is to find out the columns on which we want to apply the replace transformation or the replace function. So the columns on which we want to apply the replace function would be my NA values, right? So to flag out the values which are NA in R, we use an inbuilt function called is.na. And this dot operator means that we want to run this function across all the rows or across all the columns in a particular scenario. In this case, this dot operator means that we want to flag out the NA values across the entire data set because we are starting with our data set called air quality. So basically, this replace function here means that wherever we have an NA value across this data set, I am replacing it with 0. So if we run this command here, the data frame gets stored in air quality transform 1. So if you look at air quality transform 1, we can see that across this entire data set, wherever we had these NA values, they got replaced with 0. Now, let's say that we don't want to replace all the NA values in the dataset with 0. Instead, we only want to replace the NA values with 0 in a particular column. So let's say we only want to replace the NA values with 0 for column solar.r. So if you take a look at the dataset that we're working with, uh, we have NA values in ozone in this column. We have null values in solar.r column, and I'm sure we have null values in the other columns. But in this scenario, let's say we only want to replace the NA values with zeros in the solar.r column. So to do that, I'm going to use the if-else function or the if-else condition. So here I'm just saying that if, and like I said, is.na helps us to flag the NA values. So here in this function, in this if-else function, I'm saying that if the values, if the particular values in the solar.r column is null, if this condition is fulfilled, then I want these values to be replaced by 0. Else, if this condition is not fulfilled, then I just want to retain my solar.r value for that for that particular row. So if I run this command real quick, so if you look at the Err-Cordy transformation 2, we can see that only the solar.r column got transformed and all the other columns still have the NA values. So in this scenario, we can see that wherever we had missing value or NA value in solar.r column, they got replaced by 0, and the other values are still intact. So we haven't replaced the other values or the other non-NA values. Now, let's say that we want to fill these NA values with the mean of that particular column. Now, this can only be done when we are working with numeric data sets or when we are working with numeric columns. So let's say that instead of filling the NA values in solar.r column with zeros, we want to fill, so we want wherever we have NA values in solar.r column, we want those cells to be filled with the mean value instead of 0. So to do that, we use the across function in R. So across function helps us to apply a particular calculation or a particular function across an entire column or multiple columns. So here we use the replace. So within the across function, we use the replace.na function. And like I said, we want this replace.na function to work across the particular column. So that's why we pass the dot operator. The dot operator in R means that we want to run this across the entire column or across the entire row. So in this case, it means we want to run the replace.na function across the entire column of solar.r. And then we pass the mean function within the replace NA function. And also we want to calculate the mean for the entire column. So that's why we have this dot operator here. So we are calculating the mean across the entire solar.r column. So that's why we pass this dot operator. And we tell R basically this na.rm equal to true means that we are telling R to remove. RM stands for remove. So we are telling R to remove the missing values from the mean calculation. So if we have missing values in a particular column, then we cannot calculate the mean, right? So to make sure that in the mean calculation, we don't encounter this problem, we explicitly tell R to remove the NA values in its mean calculation. So if we run this command here, and if we look at air quality transform 3 data set here, we see that if you remember in the original air quality data set, the fifth row had explicit NA values for ozone and explicit NA value for solar.R. Now, if you look at the air quality transform 3, for the fifth row, we still have the NA value for ozone because we are not working on this column. But now in the solar R column, we have the mean value of the solar R column in place of the NA value. So wherever we had NA present in the solar.R column, it got replaced by the mean value of this column. And the mean value of this solar.R column is 185.931. So it got replaced by this particular value. Similarly, in air quality transform 2, wherever we had a missing value, it was replaced by 0. And now in air quality transform 3, wherever we have this missing value in the solar.R column, it got replaced by the mean of this solar.R column. So these are some of the practical ways in which we can work with missing values when we have numeric columns in our data set. Okay, so let's wrap our lecture by just looking at some of the basics of non-tidy data. In our previous slides, we have defined non-tidy data as messy data, but there are many instances where non-tidy data sets are used. One of the main examples of non-tidy data sets are when we are working with text data. Oftentimes, text data is not represented in rectangular format where we can use rows and columns. So whenever we are working with text data, we use the concepts of natural language processing to clean and work with text data. So we'll not go through the concepts of natural language processing in this case, but this is one of many examples of when non-tidy data makes sense. But if our data does fit into a rectangular structure made up of observations or rows and variables, then it is suggested that the tidy data should be the default choice. Okay, so to summarize our lecture here, like we had just seen in the previous slide, if our data fits into a rectangular structure made up of observations or rows and columns or variables, it is suggested that tidy data be the default choice. Once a data set is in a tidy format, it's very easy to work with the data further by using various functions in R, such as the summarize function, mutate function, ggplot function, and many other functions, as we had seen in our different exercises. There are 3 rules that make the dataset tidy. Number 1, each variable must have its own column, each observation must have its own row, and each value must have its own cell. Methods to transform a non-tidy dataset into a tidy dataset in R are using pivot functions, primarily pivot longer and pivot wider, and separate and unite functions. With this, our lecture on tidy dataset comes to a conclusion. I'd like to acknowledge Rebecca Honnold, who is a member of the Statistics Without Borders team, for creating this slide deck. And also I would like to acknowledge the Statistics Without Borders team for giving me this chance to work on this project. It was a great experience for me to create the video lecture on this topic. Thank you.